Good morning. Let's begin by looking at a quick announcement on homework 4C. Here's the problem set as it's listed on the course schedule for the semester. Problem 104, I think that was a misprint or a typo on my part. You don't need to do that problem. I mean, you're welcome to, and I'm sure you'll learn a lot by doing it, but that's actually from the rotational flow stuff that we'd covered in the previous homework assignment, and so you don't need to do problem 104. That assignment is due after we get back from spring break on Sunday, April 10th. Any questions related to the announcements or related to the material that we've been covering up until now? All right, so what is Bernoulli's equation? Let's just do a quick review before we get into the new material. This is part 2 of our Bernoulli's equation lectures. We started talking about it last time. What does it tell us? Chapter 4, we're in moving fluids. We've graduated out of static fluids, so it's about moving fluids, but what does it tell us about moving fluids? Okay, a relationship between pressure and velocity, very good. But we already have an equation that does that. We already have Euler's equation. That tells us how pressure changes when velocity changes. And so how is Bernoulli's different? If we already had Euler's equation, why do we need another one? Okay, elevation and pressure, but then again, Euler's equation also had that, because inside the term it was pressure plus gamma z in Euler's equation. And so, yeah? Okay, so I'm glad that you're remembering the limitations that it applies. So the limitations for Bernoulli's equation was an inviscid fluid, meaning one that has no viscosity, which is incompressible, and then we apply it for steady flow along a streamline. Okay, so it's a change in velocity that is relating to the change in pressure and the change in elevation. What kind of change in velocity? Maybe the clue is in the limitations when we were saying it's for an inviscid fluid, which is incompressible, along a streamline, and then the last one is steady flow. Bernoulli's equation should be applied for steady flow. What was the difference between the type of acceleration for Euler's and Bernoulli's? Okay, convective acceleration is for this one, and local acceleration was for Euler's equation. And so, you know, like when I was initially asking the question, why do we need some new equation if we already had something that told us how velocity change is related to pressure and elevation change? Well, that old equation we had is when the velocity change is due to a local acceleration. Here, it's not a local acceleration, it's a convective acceleration. So here is one of the interesting applications of Bernoulli's equation. This is a way of measuring velocity. It's a very, very simple way of measuring velocity. So let's look at this picture and try and diagnose what's happening. It's similar to one of the examples we looked at in class last time, where the streamlines are going along. They're indicating the direction of flow. What does it mean that the streamlines are parallel? It means uniform flow. It means that the velocity isn't changing with respect to position, except that between 1 and 2, one of these streamlines finds a dead end, because the water is flowing through the river, but then the water inside of this tube is static. It's not flowing. You know, we don't see at the top of this tube, it's not water is spraying out, but the water is rising to a certain point and then it stops rising. It comes into equilibrium. How is it possible? What's to explain the fact that the liquid is rising inside the tube to an elevation greater than the river's surface? Why is it going higher inside the tube like that? Okay, there's more pressure someplace. You know, we know from the hydrostatic equation that pressure increases as we go down through a liquid. So what that has to mean is that inside this tube, so if we applied the hydrostatic equation inside this tube, which we're allowed to do because inside this tube conditions are static, so it's perfectly valid for us to apply the hydrostatic equation inside this tube. So if we start here at the interface of the air and the water, the air pressure is 0. So the liquid pressure here is 0. And of course, we're talking in terms of gauge pressure. As we go down, we could find some pressure in the liquid at this point. But that's different on the inside of the tube than it is at the river, because here at the river, the air and the river are touching, and so they have the same pressure, which is 0. So there is a pressure difference here on the free surface compared to inside the tube. And so what that has to mean is that for some reason, something about this is pushing the water up. There's more pressure inside this tube than there is in the surrounding water, in the water that goes around it. So any thoughts about that? What's causing, and why is it that this tube that's in the water is experiencing more pressure? Let me ask you this. You see the way it's pointed. What if I turned it around the opposite direction? The opening of this tube is pointed towards the river, so that river is running into it. What if I rotated the entire tube, and now I had it so that the water is flowing around it, but it's not pointed towards the direction of flow? Do you think things would be any different with this water elevation? What would happen to the water elevation? It would be the same, or maybe even lower, depending on if there was a suction effect. All right? So what we sort of have the idea of is that when the streamline intercepts the opening of that tube, it causes a localized increase in pressure. And that's a stagnation point. We can call this a stagnation tube because the streamline and all of the energy in the flow runs into a barrier, the barrier being the water inside of this tube, and there is an exchange of energy. So here is Bernoulli's equation written in a different way. The way that I wrote it in class previously was like this: the pressure head plus the elevation head plus the velocity head, and then it was constant, so meaning that that's equal to the pressure head at 2, the elevation head at 2, and then the velocity head at 2. Okay, so this and that are the same, except that location 1 and location 2 are on the same horizontal plane, and so I've canceled out the z terms. And then you can see I've multiplied each term by gamma, so that we're just left with P1. And then that density term in the velocity head is because we have gamma divided by g. So that's Bernoulli's equation. And what we're saying with the stagnation tube is all of the energy that there was at 1 is also present at location 2. It's just that it's changing form. There was some velocity head at 1 because the flow is moving, but just at the mouth of the stagnation point, there isn't velocity anymore. And so the energy that was tied up as velocity is being transformed into additional pressure. And so we can use that idea with the stagnation tube. We can say, let's solve for the velocity at 1. Even though we don't know what it is, it's somehow related to the change in pressures. How much the pressure changes at 2. It went through a change of pressure because all of the velocity head was converted into extra pressure. The energy can't be destroyed, so it just has to change form. So what this next step of the equation is saying is that the velocity at 1 was transformed into a pressure increase. And now, if we look at the situation inside the stagnation tube, we can do the hydrostatic equation, and we can say the pressure at 1 is related to the depth into the water. Now, this is a little bit iffy, because this is saying let's apply the hydrostatic equation in the river, and remember, strictly speaking, the hydrostatic equation is for static conditions. So the river is moving to the right. It's not so bad for us to apply the hydrostatic equation in a river that's open to the atmosphere and going down in a direction that is tangent to the velocity. So this isn't strictly the best way to do things, but it's okay. We can approximate the pressure at a certain depth in this way. And so if we do that, then we can say the pressure here at 2 inside the stagnation tube is the hydrostatic equation through the tube. And so we can know the pressure change from here, the pressure change is just the difference between those two terms. It actually becomes quite simple. The velocity at 1 is just the square root of 2gl, where L is how high above the liquid surface the water rises. So what this really looks like to me is the straw that you get in a restaurant. Like if you're putting it into a milkshake or into a glass of soda. And what this is telling us is that it's, you can use a straw like that as a means of measuring the velocity of flow. If you point the straw in the direction of flow, it will intercept some of the velocity and the water level will go up, and how high it rises above the surrounding water tells you what is the velocity of the flow. So that's a pretty easy way to measure flow. If you're measuring a fluid that is inviscid, incompressible, and conditions are steady, and you're measuring it along a streamline. So along a streamline, that's going to be true here. Steady flow, as long as the flow rate isn't changing in the very short term between when you are taking your measurements, then that's valid. But yeah. Good question. So he's asking if the fluid isn't inviscid and it isn't incompressible, then what kind of error can you expect to see? In this case, I don't think that this is water, and so we're pretty close to the incompressibility assumption. So it won't be too bad for that. But what we're not close to when we're using water as our fluid is the inviscid condition. And so it depends on the shape of this device. So the inviscid assumption is saying the fluid has no viscosity and therefore there won't be any energy losses. So will there really be energy losses? You see how they're zooming in on this picture here? It's showing some turbulence, these little vortices and eddies around the side of the object. We could get better results if we make this very thin, or if we have a shape so that there's less of this disturbance. Because what we want is we want the stagnation point to stop perfectly, and then the streamline right next to it just slips past without any sort of turbulence or disturbance. And so, how much error we have in measuring the velocity this way depends on the shape of the tube. And so it would be kind of an interesting experience to go through the process of designing something like this in the lab, measuring, how does tapering the edge of that tube get you closer and closer to the actual velocity? Because, you could measure the actual velocity of the river in other ways. You could throw a bottle and then watch the bottle pass a certain distance and use a stopwatch. And so you could find the velocity that way and then compare it to what this is predicting. Or there are these devices that look like a propeller on a stick, and you put the little propeller on a stick down and then it spins the propeller a certain velocity and you can know the velocity that way. There's even ways of putting a loop through the water and then measuring the magnetic effect of the fluid that's passing through a loop. It's turned into an electrical current. So there's lots of ways to measure flow, but that's the long answer to your question. How much error will there be? It depends on the shape of that opening, and it could be made to be accurate enough. Within 10% would be a reasonable assumption. Okay, so here's one where they've tapered the shape of the opening. And the reason why they've done that is to try and help smooth the flow around the edge. This is a pitot tube. These are used in aircraft most commonly, and there are some other applications as well. But it's a way of measuring velocity by measuring changes in pressure. So you can see here I've put a differential pressure gauge just as a conceptual picture. Differential pressure gauges are connected to these tubes, and maybe if you've seen airplanes before, they have a little tube sticking off the front of them or off of the wing in the case of like a small Cessna. And it's just a way of measuring the airspeed of the aircraft. And the way that it works is the pressure is measured at two locations. At location 1, it's facing into the flow of the air that the airplane is flying through. And so here we have a streamline that's going to stop suddenly. And so what does that do to the pressure at location 1? It increases it. So pressure 1 we'll call our high pressure location. And then the streamline that goes around the pitot tube, here is an opening at location 2, but it's not faced into the direction of the flow. And so it's measuring just sort of the environmental pressure without any additional increase. And so at location 2, it's sort of measuring how much of the pressure at 1 is due to the normal atmosphere compared to how much of it is that additional increased pressure because of the stagnation point. So we have two different pressures, and pressure 1 will be higher than pressure 2 unless the airplane is sitting on the ground, and then they'll both be the same. But this pressure gauge here, what they do is they calibrate that gauge so that they're relating the difference in pressure to the velocity of the gas that's passing through these 2 points. So it starts with Bernoulli's equation, and what we're doing is we're looking down on this. These tubes are generally oriented so that, a plane flies horizontally mostly. If you're at an air show, you'll see them going up or going down, but the most common mode of flight is flying horizontally, and so the tube would also be pointed horizontally. So the view that we're taking right now is from above. And the reason I bring that up is it basically Z1 and Z2 are going to be equal in the case of an airplane flying through the air. So we can simplify Bernoulli's equation until we get to the form of what we're calling the pitot tube equation. Now this is different from the differential, from the stagnation tube that we were looking at before. The stagnation tube was open to the atmosphere. The pitot tube isn't open to the atmosphere. It's the way that we're measuring the pressure isn't by how high a liquid rises, but the way we're measuring the pressure is from this gauge. And so it's the difference in piezometric pressure, P sub Z1 versus P sub Z2. And piezometric pressure is something we've touched on a couple of times before. Remember, what piezometric pressure is it's the pressure plus gamma Z. And so just to refresh your memory, in static conditions inside of a tank, for instance, piezometric pressure is always constant. If we had 2 points that we were interested in, like for instance, if here is location 1 and here is location 2, we know that the pressure at 2 is going to be greater than the pressure at 1 because location 2 is deeper into the water. But Z1 is greater than Z2. And so if we keep track of both things simultaneously, P1 plus gamma Z1 is equal to P2 plus gamma Z2. In other words, the piezometric pressure doesn't change because as we go down through the fluid, we're losing Z, but we're increasing pressure. At the same rate that we were losing Z, pressure is increasing by pressure times gamma. I'm sorry, pressure is increasing by delta Z times gamma. So here's the delta Z between the 2 points. That's for static conditions. Here, when we have a pitot tube going through a gas or a liquid, then there is a change in piezometric pressure. And so the pitot tube is measuring that. So let's take an example. And by the way, here's a picture of a pitot tube sticking out of a small aircraft. And that's really the way that velocity is measured. Now, we have GPS these days, and so most likely this aircraft also has a GPS stuck onto the dashboard somewhere, or if it's a nice one, built into the system. But GPS is a relatively recent innovation. It wasn't used by the general public until the early 1990s. And so before then, this is the way that they measured velocity in an airplane, is by the pitot tube. And they're still in airplanes. Even if it does have a GPS, they still have this as a backup system. All right, so in this example, we have a certain gauge. Let's say we have a gauge and it can only measure pressure differences from 0 to 75 kPa. Now hold on, no, that's a mistake. It should be 7.5 kPa. I've just recently changed this example, so that would have been kind of a strange answer in the end. All right, so it measures from 0 to 7.5 kPa. And so what we're interested in is if our pressure gauge can measure over that range, then what's the maximum airspeed in terms of kilometers per hour that this pitot tube is going to be able to measure? Okay, so what it's saying is, you know, at 1 the pressure is going to be higher than at 2. So let's say the pressure at 2 is 0 and the pressure at 1 is 7.5 kPa. So what is the velocity that that's going to allow you to measure? And let's assume that it's horizontally oriented so that Z1 and Z2 are equal. All right, so let me bring up the lights and you can get started on trying this one out. Okay, so the question I got about the pitot tube is, where is the velocity 0? The air is moving before it hits that opening, but then when the air runs into the opening at 1, it stops. And so the air velocity at 1 is 0, and then the air is sliding past the opening at 2. So the wind speed that we're actually measuring is the air velocity at 2. So here in the equation, you're going to say V1 is 0, V2 is the unknown, and then Z1 equals Z2, and the pressure at 1 is the high pressure location, so 7.5 kPa, and the pressure at 2 is 0. So let's look at the solution for that one. Okay, so I started with a very crude drawing of the system just to remind me where is location 1 and where is location 2. The important thing to remember that location 2 is just, that opening isn't intercepted by a streamline. The streamline goes past it without being stopped. So I'm solving in terms of V2, where I put in the change in pressure on the inside of that. It works out to 111.8 meters per second. And then if we do the conversions from meters per second to kilometers per hour, it should be 402.5 kilometers per hour. Let's go back to the picture of the pitot tube. In this pitot tube, the center opening is measuring the stagnation point, and it goes all the way. If you follow the maze, the opening, which is the high pressure port, is going this way, and then we're continuing to follow it. So here is one end of the differential pressure gauge, and then the static pressure tap, which is opening to the side, is surrounding the stagnation pressure tap, which is the center one. And so this is a cross-sectional view, but what they're saying is that there is an opening on either side of it, and the entire area that's surrounding that center tube is where the pressure is lower, and so we have another opening somewhere outside, and so the difference in pressures, this pitot tube is basically designed to carry two different pressures to wherever the gauge is. The pressure that's related to intercepting the streamline and the pressure that's related to having the streamline go past it without having the velocity exchanged into extra pressure. Any questions about how a pitot tube works? Or any questions related to this example that we were looking at? All right. Well, what if we use the pitot tube in a liquid instead of using it in a gas? Just now we were working an example of measuring the velocity of air as an airplane is going through the atmosphere. We can also use it, for example, in a pipeline, because we would sometimes want to know what is the velocity of a liquid flowing through the pipeline. So in this illustration, what we have is liquid is flowing from top to bottom inside of a pipe. So this pipe is vertically oriented, and it's actually kerosene that's flowing through a pipe. So the kerosene is flowing down, and inside of this, this is a manometer instead of just a pressure gauge. You know, we can use a manometer as a way of quantifying the pressure where we look at the deflection. Why do we use mercury in manometers? What's the advantage of having a very dense fluid as our manometer fluid here that's indicated in the blue shaded? That's right. We won't have to have a huge deflection because the fluid is so dense, then that means a relatively small deflection is going to be appropriate for a bigger pressure increase. So that's why we would often see mercury used in a manometer like this. Okay, so let's follow the pressure. So velocity is moving along, it reaches 1, and there's a stagnation. So if we go down through this tube, this is where the stagnation tube is connected to. So there's more pressure at 1, and so it's pushing this liquid down. There's a deflection in the mercury because the extra pressure at 1 is pushing down on this side of the mercury. And then there's less pressure on the left side of the mercury because that's what's connected to location 2, which is just looking at the flow from a sideways perspective where there is no additional pressure due to the velocity stopping. Okay, now here is the Pitot tube equation, which we have written in terms of the piezometric pressure. Okay, so piezometric pressure is, if you remember, it's the pressure plus gamma z. And so P sub z1 is going to be the pressure plus gamma z for location 1. And what we're going to need to do to solve this problem, we're trying to find out what is the velocity in the pipe. That's the main unknown of this problem. That's why we would have this, is we're measuring a deflection here of 18 centimeters. So if we have this y equals 18 centimeters, then from that we should be able to tell what's the velocity of kerosene going through the pipe. And one of the important keys is that we don't just have the pressure automatically given to us. We have to use the manometer equation between 1 and 2 through the Pitot tube. And so let's start with that. We have the pressure at 1 plus, now we're going to be going down through the inside of the tube, and part of the time it's going to be kerosene, and part of the time it's going to be mercury. And so we're going to have two different unit weights. There's going to be, I'm going to call it the unit weight of kero, meaning kerosene, and then another one of our unit weights is going to be the unit weight of Hg, which is the abbreviation for mercury. Okay, so we've got the pressure at 1, and then we go down some distance. The first distance that we go down is Z1 minus Z2. That's just some distance that takes us from 1 to 2. And inside the tube, there is kerosene. So it goes down gamma kerosene. Okay, so then that gets us inside the tube to this location. And we want to go all the way down through the tube and back to 2. Okay, so now we're going to go down, and so the pressure is increasing, and the distance we're going is L, and we're still going through kerosene at that point, so times the gamma of kerosene. All right, so now we are at this interface. We're going to jump over here, the pressure is equal. Now we're going to go up through the mercury, so minus, and the distance is y, and we're going through the gamma of mercury, which puts us at this interface, and now we're going to have to go up some distance to get to 2 through the mercury. What's the distance that we're traveling upwards through? L minus y. You guys got that quickly. So minus L minus y is our distance, and the fluid that we're going through is kerosene. And all of that is now equal to P2. So that is the manometer equation through the pitot tube. Yes? Okay, so he brings up a good point. Why didn't we do it 1 and 2 are close together? So why didn't we just say P1 plus gamma of kerosene, Z1 minus Z2, and so now we're at P2. Why couldn't we do that? It's not static. If we did this, basically what we'd be saying is we're going outside of the pitot tube from 1 to 2. If we look back at here, so the way that we're getting from 1 to 2, basically, just in conception, is we're starting at 1, they're not connected, not directly. So to get to 2, we have to go through here, through the gauge, and then back through this direction. When we apply the hydrostatic equation, we can't go through the moving fluid, so we can't go on the outside of the tube, because then that's not static conditions. So if we want to go from 1 to 2 and apply the hydrostatic equation, we have to go all the way through the tube and through the gauge to get there. And so that's what we're doing in this illustration is there's not a gauge, but there's a manometer. So to get from 1 to 2, to relate the two pressures, that's why we're doing that, is to say what is the relationship between the pressure at 1 and the pressure at 2. We're going all the way through the pitot tube and through the manometer, taking the scenic route, as they say, to get from 1 to 2. All right, so we've written the manometer equation between 1 and 2. Here's the next thing that you need to do. Cancel out terms, and I'm not going to do this on the board. I'm going to give you the time to do it. There's a few terms that will cancel out. Yeah, you're going to see some terms cancel out, and then you're going to want to rearrange this equation in terms of P sub Z1 minus P sub Z2. Remember where P sub Z1, what we mean that is P1 plus gamma Z1, and so on. All right? So let me get you started on your problem solving, and I'll be circulating around with the solution for this one. What becomes tricky about this problem isn't necessarily the fluid mechanics, but it's maybe the algebra. Let me show you what I mean. All right, so here is the manometer equation. We went through the first part pretty thoroughly together, like where the P1 plus gamma of the kerosene times the difference in elevation. This first line we just created by going from 1 to 2 and applying the hydrostatic equation through each of the steps. So I think everyone's on the same page on this first line. But what I've done in the second line is I've expanded all of the terms out. So gamma times z, gamma times z. I expanded everything out so that I can cancel these two redundant terms. And then also it makes it easier to see the grouping it by piezometric pressure. So I rearrange it so that I've got pressure at 1 plus gamma of the kerosene times Z1, because that I'm going to call P sub Z1. And then I rearrange it so that I have these terms together, the P2 plus gamma Z2. So that's my piezometric pressure at 2. And the advantage of doing that is that when I go into the pitot tube equation, I don't know the actual pressures at 1 or 2. But I do know the difference in piezometric pressure, because by rearranging the manometer equation, what I have is that the change in piezometric pressure, that's what the manometer itself is measuring. The manometer isn't only measuring the change in pressure, it's measuring the change in piezometric pressure. And so Y times the difference in the unit weights is what I'm going to substitute into the pitot tube equation. So here in the second part of the problem, I'm given the pitot tube equation. That's, something we derived earlier today's lecture. And so I make the substitution, this Y times the change, the difference in the unit weights that is what I got from the manometer equation as the difference in piezometric pressures. So then once I've made the symbolic substitution, then I make the numerical substitution. So here's the difference in the unit weights, here's the deflection of 0.18 meters, and it gives me 7.47 meters per second is the velocity. So this isn't something, when I was looking at this example several semesters ago, it's not something that made immediate sense to me. It's something that I had to sit and look at for 15 or 20 minutes. You've only had 10 minutes to look at it. So if you're still a little bit confused, take some time later today and look at it some more. See if you can start at deriving the hydrostatic equation yourself from 1 to 2 and then rearrange the variables. If you're still feeling a little uncertain about this, just takes the extra time. I want to give you some tips on a homework problem. I'm not going to see you again until after spring break because today's Tuesday and we don't meet on Thursdays. So you've got a long time between when we meet again. So here's some key ideas from one of the problems that you've got. We've got stagnation tubes that are measuring a difference in pressure. And what these stagnation tubes, also known as piezometers, what they're measuring is not just the pressure itself, but they're measuring the piezometric pressure. Now think about it conceptually. What if the water, there's water flowing through this, and because the throat is necking down, then that means that you've got a higher velocity at 2 than you've got at 1. And so when you have higher velocity, the pressure will be lower. That's why there's this deflection here. But if there was no velocity, like if the water stopped, then those two liquid levels would be the same. It's only when the velocity starts to move through them. And so remember that these are measuring piezometric pressure, and so the definition of piezometric pressure you can get by grouping the terms like we just did in this example just a few moments ago. If you rearrange Bernoulli's equation in terms of P1 plus gamma Z1 and then minus P2 plus gamma Z2, then on the other side of the equation you're going to have the difference in velocities. So I just wanted to remind you that this example has many of the same problem-solving steps as what we just solved, even though instead of a differential manometer, this is just a piezometer. Okay. Well, I hope you have a great spring break. Of course, you've still got the rest of the week to get through it, but I won't see you, so enjoy that. And when we get together on Sunday the 10th, you'll have homework 4C to submit. So I'll see you then.